Hello, AP Chemers. Hope you're having a wonderful day. Today we're going to talk about ionic bonding and more specifically lattice energy. So we'll start with the definition of lattice energy. Lattice energy is the energy that's released when cations and anions form 1 mole of an ionic crystal. So let's write that down. So again, it's the energy that's released when cations and anions combine to form 1 mole of an ionic crystal. Now, that's not the official definition, but that's the definition I like because it explains it a little bit better. So what this means is, let's say that you have Na pluses and Cl minuses, and the sodium is already with a positive, so that means it already lost its electron. The chloride is already with a negative, so that means it's already gained an electron. It already has its negative. So this is how much energy is released when those two combine so that you form a solid crystal, 1 mole of that solid crystal. The reason why energy would be released when those are combined is because there's positive and negative attractions between them, Coulombic attractions between them, and so it takes a lot of energy to keep them far apart. It will release energy when you combine them together to form that crystal. So it is the energy that is released when you have enough of your ions forming a solid crystal and forming 1 mole of that. Now, in order to form an ionic substance like NaCl, you have to get the sodium to be Na plus, and you have to get the chloride to be Cl minus, and then you form your crystal. And so the Born-Haber calculation, or in other words, the Born-Haber cycle, is a series of steps, kind of like using Hess's law to show steps in order to get to forming an ionic compound. So if I wanted to calculate how much energy is involved to take, my elements in their natural state to form 1 mole of my ionic compound, these are the different steps that I would have to go through. So first, I have to prepare my sodium. So in order to prepare my sodium, first I have to turn it into the gaseous phase. And so the first step would be to take neutral solid sodium and to turn it into sodium gas, which would be sublimation. So delta H of sublimation. And that number is given to me as 108.4 kilojoules per mole. Now that number is a positive number because sublimation would be endothermic. In order to go from a solid to a gas, low energy to high energy, you have to absorb energy, and so that should be a positive number, endothermic. Next, now that my sodium is in the gaseous phase, I can now remove an electron to form sodium ion. So I can take my sodium in the gaseous phase and I would add energy to it in order to get sodium ion plus an electron. Like we said, that would be endothermic. This is the delta H of the ionization. So we're ionizing the sodium. And it is positive. They give it to us as positive 495.7 kilojoules per mole. So now my sodium is ready. It's in the gaseous phase. I had turned it into an ion. So now let's take a look at my chlorine. Now chlorine exists as diatomic, and it's in the gaseous phase at room temperature, so no need to sublimate there. It's already a gas. But I can't use diatomic chlorine. First, I have to break the bond between those two chlorines. So, this really looks like a Cl bonded to a Cl, so I need to break this bond. Remember, you have to put in energy in order to break a bond. So that is also endothermic. So let's show that. So Cl2, breaking that bond to get to 2Cl. And I only need one chlorine. I don't need two of them. So if I half this reaction, so it's really half and 1, then that would be what I need. To break that bond, this is called the dissociation energy. So delta H of dissociation. And we said it's endothermic because I have to put in energy in order to break that bond. The heat of dissociation of chlorine is 243.3 kilojoules per mole. But just like we divided our reaction by 2, I will also divide this heat by 2 as well, because I only need one chlorine, not both chlorine atoms there. Now that my chlorine is dissociated, I can now add an electron. Remember, the energy required to add an electron is called the electron affinity. So I take my chlorine and I add an electron to get Cl minus. And usually that is exothermic. When you gain an electron, the atom will release energy. And it's called the affinity, the heat of affinity, or electron affinity of chlorine. And it is indeed negative. It's negative 367.7 kilojoules per mole. Okay, now I have my Na plus ready and my Cl minus ready. One last step that I need to do is to take my Na plus and my Cl minus ions and combine them to form my solid crystal. And that is your lattice energy. So our last step here would be to take my Na plus and my Cl minus and form solid NaCl. And this is your lattice energy. Lattice energy is always negative when you form your crystal, again, because that's favorable since the ions attract each other because of the Coulombic forces. That's going to release energy. And it is negative 779.0 kilojoules per mole. So just like we're used to with Hess's law, let's try to add these reactions together. So let's see if we can find anything on both sides that we can cancel. So sodium gas is here and sodium gas is here. I can cross those out. Na plus and Na plus, electron, electron, Cl and Cl, Cl minus and Cl minus. So what do we have left? We have Na solid plus half Cl2 yields NaCl solid. I've taken my elements that are in a natural state and formed 1 mole of my ionic substance. And so if I wanted to figure out what the energy associated with this process, with this overall process is, all I have to do is just add up my delta H's here. So if you look at this process, this is the formation of sodium chloride. So I wrote delta H of formation here. And the total altogether is negative 421 kilojoules per mole. So overall, it's an exothermic process. Let's try another example. This time we're going to calculate the enthalpy of formation of barium chloride. So barium is a solid at room temperature. Chloride, we said, was diatomic gas. And we're trying to form 1 mole of barium chloride. So first, we're going to start by preparing our solid metal. So first we're going to sublimate it. So let's write the sublimation equation. So we took barium solid, turned it into barium gas, and again, that would be an endothermic process. The delta H of sublimation is 178 kilojoules per mole. Next, we're going to take our barium gas, and we are going to ionize it. So we're going to remove an electron. So we got to add energy to remove an electron. Now if we do, we're going to get BH plus and an electron. That is endothermic. Heat of ionization is always endothermic. And that would be our first ionization, removing our first electron. So that is 503 kilojoules per mole. Then we can take our Ba plus and add some more energy to remove a second electron because we want the barium to be a Ba2 plus, and removing another electron. This is also ionization energy, but this is the second ionization energy. And that is also going to be endothermic, and it's going to be a higher number. Remember, it takes more energy to remove the second electron. It is 965 kilojoules per mole. So now our barium is ready as Ba2 plus. So then we're going to move on to our chlorine to prepare it. So first we need to dissociate the bond, break the bond between the two chlorines here. So let's do that. So my chlorine, I break the bond between them to get two chlorine atoms, and that would be equivalent to the bond energy. The dissociation energy is the same thing as the bond energy of the chlorine breaking the bond. So when we form this bond, it would be negative 239 kilojoules per mole. When we break it, it's positive 239 kilojoules per mole. Now this time we do not need to divide by 2 because we do need both chlorines to form the BaCl2. So we'll leave it as is. But we do need to take my chlorine that's associated and add electrons to it, so we get chloride ions. And we need both of those, so we need two of them. So we'll say 2Cl plus 2 electrons yields 2Cl minus. And this would be the affinity of chlorine. Now the affinity of chlorine is given to us as negative 348 kilojoules per mole, but that's for just one chlorine atom to become Cl minus, to gain that electron. We have two of them, so we need to multiply that number by 2. So here's my number multiplied by 2. So now my barium ions are ready, my chloride ions are ready. All I have to do is combine those to form the crystal, to form the solid lattice crystal. So let's do that last step. So we're going to take the Ba2 plus and 2 Cl minuses and form BaCl2 solid. That is your lattice energy. And that is always exothermic. In this case, it's negative 2,056 kilojoules per mole. So let's add our reactions together to see whether we are going to get the formation equation for barium chloride. So let's say we have barium gas and barium gas. Those cancel. Ba plus and Ba plus. Ba2 plus and Ba2 plus. 2Cl and 2Cl. 2 electrons on this side, and then here's one, and here's another one. And then the 2Cl minuses. So what we have left is Ba solid plus Cl2 yields BaCl2. And so the heat of formation for this would be equal to, so when you add all these delta H's together, you get the delta H of formation as negative 867 kilojoules per mole. So again, the Born-Haber cycle is a way for us to calculate the heat of formation of an ionic compound. It's not necessarily that these things happen in this order, but these are steps that if we add them up, we would get the formation equation, and therefore, if we add the delta H's, we would get the delta H of formation. So it's a way to calculate things. It's not necessarily how these ionic substances actually form. So we said that lattice energy is the energy that's released when an ionic compound is formed. And again, here's my definition that I prefer. It's the energy that's released when the ions combine to form 1 mole of a solid ionic crystal. So we've already had our cation form, our anion form. We're just putting them together to make it into a solid crystal. So let's talk about what would make this energy that's released higher or lower. What changes the magnitude of this energy that's released. So remember that the energy that's released is because you have something that's positive and something that's negative coming together. So like we said, let's say we have Na pluses and Cl minuses, and we want to combine those together. There is an attraction here, the Coulombic attraction. So remember that Coulombic attraction, Coulomb's law from last chapter, had to do with the force of attraction and repulsion between the charges. Remember that it has to do with charges, and it also has to do with the distance. So if you recall, the force of attraction is proportional to the charges over the distance. So this attraction, if it's stronger, more energy will be released. Well, the attraction will be stronger if, 1, the charges are higher. So for example, let's say I have, instead of Na plus and Cl minus, what if I have Mg2 plus and O2 minus? Which one would have a higher attraction? This one would have a much higher attraction because you have +2 and -2 versus +1 and -1. So the charges matter. The higher the charges, the more the attraction, and therefore the more energy released, or the higher the lattice energy. The other thing that matters would be the distance between the ions, and the distance between the ions will have to do with the radius of the ions. So let's say you have, for example, an NaCl versus Li plus and F minus. So lithium fluoride versus sodium chloride. There's obviously an attraction between the Na plus and the Cl minus, and then the Li plus and the F minus, but there would be stronger attraction in the lithium fluoride because lithium ion and F minus ions are both smaller than Na plus ions and Cl minus ions. So the smaller your radius and the higher your charges, those would mean higher attraction and therefore more energy released, or higher lattice energy. So again, the higher the charges and the smaller the radii, the higher the lattice energy. Now, what if you have higher charges but bigger radius? Or smaller charges but smaller radius? So then what? Well, the charge definitely trumps the radius, or the distance. So let's write that down. Charge trumps radius or distance. And so the one with the higher charges will always win. So let's look at some examples here. It says, which would have the most exothermic lattice energy? Explain why. So that means which one would release the most energy when those ions combine. So let's look at these. We have LiF and CSF. So the first thing you want to do, charge is the most important thing. So you want to assign charges. So Li is +1, F is -1, CS is +1, F is -1. So my charges are the same. If my charges are the same, then I look at the distance. Which one is smaller? That would be the LiF. Smaller radii, same charges. Let's look at the next one. We have Li2O and Na2S. So first, assign your charges. So +1 and -2 versus +1 and -2 again. So same charges. So then you look at the radii. And so Li2O is smaller in radius than Na2S. Okay, let's look at the next one. The next one is Na2SO4 or CaSO4. So this is +1, -2, +2, and -2. No need to look at the radius. This has higher charges, so that trumps the size no matter what the size is. Higher charges. Okay, so we said that when we combine our cation and anion to form the solid, so when these two combine to form a solid crystal, energy is released. Well, what if I already have a solid crystal? Let's say I have some potassium chlorate. I'm doing the Screaming Gummy Bear demo, and I want to melt it. Well, what happens with melting? Melting means that you are breaking the crystal, breaking the solid crystal and making it into a liquid where the ions are able to slide around each other. And so I'm breaking the crystal lattice, which are intermolecular forces. I'm breaking those. That's a physical process. And so in order to break that crystal, you gotta use energy. So for example, if I want to melt my potassium chlorate, I have to heat it up so that I am providing energy to it in order for it to melt, break that lattice crystal. And so the energy that's needed in order to break the lattice and to melt my solid would be the same magnitude as the lattice energy. It's just going to be the opposite sign. It's going to be the positive sign. So again, if I had a bunch of Na pluses and Cl minuses, and I want to combine those together, get them close to each other to form a solid crystal, that would be a physical change, and the energy would be exothermic. It will be released, and it would be negative, and it's called the lattice energy. If I already have my Na pluses and Cl minuses already as a solid, and I'm trying to break that crystal so my ions would dissociate, then that would be the same lattice energy, but this time because I'm breaking that crystal, I have to put in energy, so it's the same magnitude, but the opposite sign, it'll be endothermic. So let's show it as this. When I combine those, that's your lattice energy, but it's going to be negative. This is also the lattice energy, but it's going to be positive when I melt it. So this is forming the crystal, and this is melting the crystal, or breaking the crystal in order to melt it. So this question is asking you which would have a higher melting point. Well, higher melting point means I need to heat it to a higher temperature in order to get it to melt. So that means if I have a higher melting point, there are stronger intermolecular forces that I need to overcome. There is a stronger lattice energy that I need to break in order to melt it. So whichever has the higher lattice energy is going to have a higher melting point. So let's look at these here. So I have NABR and NAI. Remember, when it comes to lattice energy, what's the most important thing? The charges. So +1 and -1. This one's +1 and -1. So same charges, same cation as well. They're both Na pluses. So the only difference is the anion. There's Br minus and there's I minus. The one that's smaller is going to be attracted more. And so NABR has a smaller radius, and therefore it has a higher lattice energy, and therefore I need to heat it up to a higher temperature in order to break that crystal. Okay, let's look at the other example here. We have Kf versus K2O. So assign your charges +1 and -1. This one's +1 and -2. Different charges, no need to look at the radii. This has higher charges. So that crystal is attracted, the ions are attracted to each other more in that crystal, and so it is harder to break that crystal in order to separate those ions, and so therefore K2O would have a higher melting point. All right, that is it for today. Hope you have a great rest of your day.